I think even welding in the aerospace industry is a little too broad. And you don't have to do welding. You could do machining in some industry. But actually, I'd sort of rather you take something that's hard to machine, like a carbide tool. It's hard to machine. You got to machine it with diamond or boron nitride. And what, you know, or I'm going to machine something that's super hard, okay? And there are super abrasives. I mean, if you explain to the class when you use diamond and why you don't like to use diamond on machining of steel, because the carbon diffuses in. You like to use boron nitride because steel doesn't diffuse. When it gets hot at the cutting surface, boron and nitrogen don't have high solubility in steel. I mean, I'm not saying that's the thing, but you should take something that's fairly specific, fairly narrow. If you want to do something big and broad, then we can set up and you can do a 1-hour seminar for the class. No, seriously. I mean, I'm not trying to be funny here. You can't do welding in the aerospace industry in 10 minutes at anything except the most superficial level. Okay? Actually, if you're interested in that topic, I have a former student who wrote a paper with me about that. They won an award in Spain. In Spain? Anyway, that's where the conference was. They're going to be the first week or two in April. It's going to be just after spring break. I'd like to have them done by mid-April. By then. Oh, we're done with the classes a week from Monday. There'll be a class every day next week. I'll be lecturing like 3 days next week. Dr. Belmar 2 days next week, and then Dr. Belmar on the 3rd. I'm going to be gone 3rd through 5th, but if people want more time, we're going to see where I am when I finish up next Friday. And if you want more time, I'm happy to come in on the 6th and 7th of March if you haven't heard enough stories. I got more stories than you got time. Okay? Okay. Any other questions? Okay? Anybody? Other questions?
So it's more of a like kind of literature review kind of thing than
No. You could talk about your thesis. One student wants to talk about something. She made a presentation in another class and double dip. It's okay. It's okay. I don't mind double dipping. I did it all the time. I do it all the time, okay? So how can I? No, I'm not trying to embarrass you. But last semester we had several people do things that they had presented in other things. The easiest thing, well, I want you to pick a topic that you're interested in, because, and I was doing this in welding once with a bunch of Navy guys, and one guy decided he wanted to opt out of the Navy when he could, and he wanted to do masts on sailing vessels, which is not exactly the Navy. They don't have a lot of masts on sailing vessels anymore, except the Constitution. But anyway, another one wanted to do the failure of the American Airlines flight over Brooklyn, that the composite tail rudder came off. What did that have to do with welding? Well, I mean, I don't know. I don't care. I mean, this is your chance to tell me something that you're interested in. Were one of you the ones that did doorknobs? How to manufacture doorknobs a few years ago? Anyway, I can't remember. But one student was interested in decorative doorknobs. And so she came in and talked about how you make decorative doorknobs. Okay, that was when I was teaching a casting course, and it sort of fit in because the decorative ones are often cast. If you have a question, I mean, if you want to sit down and talk about it, but I'm happy to discuss it, but you will do the best job on something you're interested in, or something you want to learn about, or something you already know about, okay? But I want it to be fairly specific, okay? So talking about decorative doorknobs is fine. Anybody else want to remind me about what you talked about in the past or something? No, it doesn't have to be. It's preferred. I mean, this is a welding module, but you could be taking one of the other modules, right? So I'm not that picky, okay? We only do this for fun, okay? Yeah. Oh yeah, don't worry. We'll accommodate any of those things. I will hopefully, probably sometime next week, try to pick days in potential schedule. If not, sometime before spring break. I got to do it before spring break. Give people a potential schedule. And what you're going to do is say, I'm going to be gone that week, you know, and can we do it? And I'm probably going to be gone some of those weeks too. That's one of the reasons I don't want to give you the schedule quite yet, because I don't know what my first half of April is. Okay, but I'll know better in a couple of weeks. So we're going to be flexible on schedule and stuff. I've never had a problem with. We'll accommodate your schedule. Yes. What else? Anything else? Okay. Good. So let's start talking about. We talked about stress relief heat treatment. This is a company called On-Site Stress Relieving Services, and I meant to print these out before the last class, but I didn't. Here's a vessel. Here they built a box that's on rails. The vessel is too heavy to just put on rails. It was easier to put the furnace on rails and just slide the furnace over the vessel, and you raise this thing to 1200 degrees. Okay, there are lots of different ways to do this for on-site stress relieving. Here's a vessel that they just wrapped. They put electrical blankets around it, virtually over everything, and then they just wrap the whole thing in insulation. Here's another one down here. So if you go, there's a bunch of pictures on the web of on-site stress relieving, and it has to be done. You either have to do thermal stress relief or mechanical stress relief if the things get very large, because the residual stresses get to be huge. I told you the story about the big, well, I showed you the weld with 400 little welds in it. The big thing came off of a 7,500 ton forging press. They didn't do proper preheat or post-heat. They didn't stress relieve. They didn't peen, you know, which is you hit it with a little hammer every half inch of weld. You go in there and beat the surface to introduce mechanical stress relief by deforming the surface, which is the way we used to put together battleships with 14 thick inch armor. No one remembers how to do it exactly, and no one wants to go out and build a battleship to prove how to do it. Okay, we don't really know how to weld 14-inch thick armor steels anymore, because all those people are dead. And I don't know if I told you the story. Did I tell you about the battleship Iowa down in Puerto Rico, and the guy, one of the sailors, was upset with one of the other sailors, and so he set off a shell in the turret and destroyed the turret. The Navy didn't know how to repair it. Of course, you don't need 16-inch shells anymore. They were firing shells that had been made in World War II, and the last time I think we fired shells was in the 1970s. They were sitting off Israel, and they were lobbing them into Palestine or somewhere, Syria or somewhere. Was it Desert Storm? Okay. The Missouri was the last battleship. Maybe the Missouri was the last one built during World War II. That's why they had the signing on the Missouri in Tokyo Harbor. It was the newest battleship. Oh, you want to go in there with your newest machine. Okay, if you're going to sign an armistice or whatever. Anyway, but yeah, the Missouri, I think the Iowa may have been finished after World War II. I think it may have been the last one. But anyway, they're getting to be old ships and old rusty and everything else. But we lost the technology. To tell another story on big heavy stuff, I mentioned a big forging press. Well, the Air Force, after World War II, wanted to build fighter jets, and they wanted to build bigger ones for bombers and everything else, and they needed big forgings because no one trusts a weld in an aircraft. Okay, you haven't had the beginning of my welding course where I say the number one rule of welding is to avoid all welds possible. Okay, things will fail at the welds because they're placed at the most highly stressed location. So the Air Force doesn't trust welding, and they had these huge forgings. Well, they need forgings the size of this room, okay, the width of this room, for things like the wing boxes on swept wing fighters and stuff. And so the government helped Alcoa and a company called Wyman Gordon both build in the 1950s. They both had a 50,000 ton forging press. These were the largest forging presses in what we used to call the free world. I think the Soviets may have had a larger one. The Air Force was considering building an even larger one. The problem is these things are so big. They had picked out a mountain in Colorado that was solid granite or whatever, and it was going to be the foundation. because you couldn't you couldn't afford to pour enough concrete for these things. But one of them is still here. It's in West Grafton, Massachusetts, near Worcester, and the other one's in Cleveland at the Alcoa plant. And I was at the Alcoa plant once. The Alcoa plant, they still forge big aluminum things for aircraft and things. But what happened at the Wyman Gordon plant, they had the press goes up about 3 or 4 stories above the ground. When you walk into the plant, you got these great big 4 rods. I'll just draw 2 of them. You got the ground, and this goes up about 3 stories. Okay, 30, 40 feet high. And you got this big set of beams up here. There are like 6 of these I-beams, and they're 10 feet high. That's a story right there by itself. And they're 10-inch thick web, and they were welded together out of big forgings. I mean, this is not a rolled beam, okay? This is 10 feet high and 10 inches thick. And they were about, I don't remember, 50, 60 feet long. And you couldn't make the whole thing really as a whole forging itself, because you didn't have a forging press this size until you built the forging press. Anyway, they went 6 stories into the basement. Okay, you had this anvil down here that was a huge anvil. Okay, huge anvil that you're going to press against. But for all the hydraulics and other stuff, you basically had this thing going 6 stories down into the basement in order to run these. This thing has to move up and down, right? So you got to have another 3 stories going down, and then you got all the other stuff. Well, the other I-beams down here, which were the same as that, were 6 stories buried in the ground. And so one of them developed a crack all the way through. Someone was down there doing an inspection. They said, "Oh, I see a crack. It's 10 feet long." Okay, and they said, "That's not good." And they had 6 of these beams. Well, they had to shut down the machine. Well, it turns out the beams actually from the side had a taper to them, like this. And what they had done is they had welded on a little pad to erect this thing. When you're trying to put it in the pit down here, they had pads on either end just so you'd have something to sit on, because this was a slope 45 degrees. And they had welded these on. They were about the size of my notebook if you made it into a cube. Okay? They were not small. Okay? They were about 10 inches wide and stuff. And they had welds on there that were 2-inch fillet welds, which means they had yield level residual stresses. Right? And after about 20, this occurred in the mid-80s, so after 30 years of use, they developed a fatigue crack that started at the toe of one of these and went straight through it. 10-foot crack. Well, to build a new one of these, they estimated, would cost $2 billion. This is the whole thing. $2 billion. Because it's not just the machine, it's all the hydraulic pumps and everything else. It fills a whole building, okay, a huge building to do this. And we only own 2 of these in the United States. One at Wyman Gordon, which is now bought by the Germans, okay, and Alcoa owns the other one. Anyway, it was because of weld residual stresses. It wasn't a hydrogen crack. It was 30 years old, but it was weld residual stresses and the stress concentration. The fatigue crack went through here, and I got to go down in the elevator and see this thing. It's a little bit greasy down there. Okay, it wasn't about 2 inches of grease everywhere. Okay. But they had an elevator to go down there. And I looked at it, inspected it, and they said, "Well, how do we weld this?" And I said, "Well, you're going to have to preheat it." Anyway, I went through and helped them we talked for a couple of hours about what you might have to do and how you're going to stress relieve it. And I said, the best thing for stress relief is if you can put it in a furnace, right? Well, can't we do it in place? Because it's not the easiest thing in the world to get a 50-ton beam out of the 6th floor basement when the only access you have is an elevator shaft. Okay? In fact, they were going to have to disassemble a fair amount of this forging press in order to even get the beam out of there. Eventually, they did decide to spend the millions of dollars to rig it out, weld it, stress relieve it in a furnace, and put it back in. Cost tens of millions of dollars to make that repair weld. Yes. They had to grind the crack open. I mean, this is a 10-inch thick, so this is going to be a 10-inch thick weld. So you got the two pieces, and you're going to have to prep the ends. And so we discussed weld prep. Okay, you saw the one that I had that I passed around, and you don't do a 45-degree angle because then you're going to be putting in tons of weld metal, right? You do how narrow a groove, and should you do a straight bevel or can you do a compound bevel? Okay, where you have two different angles that you machine on here, or you do a J groove, or there's lots of things you can do. But those are we were talking about how to minimize the amount of weld metal, but still have enough fusion on the, have enough angle that you still get good fusion. Go to straight size weld, you won't get good fusion. We do have something called narrow gap welding. The Japanese spend a lot of time and money on narrow gap. We use it on the surfaces of aircraft carrier. The top deck of an aircraft carrier is 4-inch thick steel. Okay, and so we use narrow gap processes, but you got to develop the procedure. It could take you a year to develop a good, reliable narrow gap procedure. Yes, Jonathan. They could. A new forging will probably have a 1.5-year lead time. Okay, and they thought about that, but they didn't want to be down for a year and a half. Okay, they got all this turned around in about 3 months. Okay, but I mean, they're doing all the economic analysis on, well, do we go buy a new one? But buying a new one doesn't solve it, because it was still welded together up here too. The flanges were welded to the beam, so you still had to weld the thing. And the thing is, it had been welded in 1950. In fact, I found an article in 1954 in the Welding Journal that talked about this, because it was such an unusual weld at the time. They made a special feature article in the Welding Journal about building these presses. Well, come 1985, when we need to weld them again, okay, we had to find out. So we were going back and looking through the literature to see what we could find about, what procedure did anybody use. They had lost the procedure, okay. It can take months to develop a procedure. Well, it did take. It probably took us a month, and it wasn't just me. I mean, they must have brought in half a dozen consultants, because it was tens of millions of dollars. Okay. Yeah. What other questions? Yep. Oh, this forge will do titanium, steel, whatever you want. Okay. It's just 50,000 tons. Once you got a 50,000 ton hammer, you can put anything under there. It's just a question of what dies you put in and how fast you run the I mean, you change your parameters for forging aluminum. Right now, they forge aluminum because there's no application that I know of for, well, actually, there are applications for huge steel forgings, like the tokamaks. These guys will probably buy time to do a stainless steel, a 50-ton forging of stainless steel. So this forge shop, which is now owned by the Germans, Krupp, bought it, they'll forge anything for a price. Okay. Actually, not this particular one, but this forging facility in West Grafton, which used to be called what was its name before Krupp bought it? It was Wyman Gordon. Okay, it was Wyman Gordon. So Krupp buys Wyman Gordon. And Wyman Gordon at the time was forging crankshafts for airplanes, Lycoming and there's Textron Lycoming, and there's Teledyne Continental engines. If you're a little small aircraft pilot, like a Piper, Cub or something, you have these $500,000 engines that are aluminum. In fact, I'm going to talk about welding the aluminum cases on one of those when I get to the aluminum. Anyway, they have steel crankshafts because you need the strength of steel. You don't want the weight, but you can't get anything else that has the fatigue life. And Krupp buys Wyman Gordon, and they start looking at the order book, and they see, oh, well, we're making, how many? I don't know. They might make 2,000 crankshafts a year for Continental and Lycoming, and they said, we don't want this liability. We don't make enough money on 2,000 of these things to be able to, if one of them fails, you got a $10 million lawsuit. People just there are people out there who just love to sue any manufacturer of an aircraft, okay? And we could talk about that for half an hour, but Congress passed a law in 1992 or so called the General Aviation Revitalization Act, because all the Piper and Beechcraft and Cessna and all these companies were going bankrupt with all the lawsuits. Whenever some guy fails to maintain his aircraft and ditches it, okay, and kills himself and his family or whatever, and maybe some other people, some attorney comes in and sues them. And they get tens of millions of dollars in front of juries because no one wants to even think about falling from the sky, right? And anyway, so Krupp looked at this and said, we don't want this liability. We can't make enough money off the few things that we're selling. And so they gave 1 year notice. They couldn't just cut them off because that would be restraint of trade and they could be sued for, because they gave them 1 year to find another supplier. And so they found a company down in Kentucky that had been manufacturing crankshafts for International Harvester engines, the big trucks going down the highway. And those guys were looking for business, and they said, sure, we'll forge your crankshafts. The problem was they didn't have quite as good a quality control, particularly since they were building a new plant. And so in the process of building the new plant, they weren't paying too much attention about what was going on in the old plant. And they produced about 3,000 crankshafts for Teledyne Continental that Teledyne Continental had to go out and do a recall on. Okay? They had about 10 failures. Only 1 or 2 killed somebody, but even so. So there's a certain liability that you have to worry about in these businesses, and the Germans didn't want the liability, and they were probably right. It's who are you going to find who wants to do this? So you often run into these questions about, you don't want to sue someone in manufacturing because you're liable to put your supplier out of business. Okay? So a lot of times, you just sort of eat the cost of these lawsuits without passing them back to other people who screwed up. Yes? Other question? No. Just people scratch. A lot of scratching out there. Okay. Okay. So anyway, I wanted to talk about, well, I think I told you enough about that one. That was they left a detail on there that created a stress concentration when everybody thought, well, it's not loaded. Well, it is loaded, and there was a stress concentration, and it did create a problem. And they did fix it, but they had to post-weld heat treat it in a special furnace. Now, we've talked about preheat. We haven't talked as much about post-weld heat treatment. But in post-weld heat treatment, I think I may have actually told you that for post-weld heat treatment, I must have told you this. There are 3 reasons to temper the steel for low hardness. You lower the hardness, and I like to just call it HV, which Vickers hardness, but it can be Rockwell C, whatever. But anyway, you temper it, you relieve residual stresses. And the third thing you do is you eliminate hydrogen. And so on this one, if you think of the Venn diagram, I remember I had a little circle, and a little circle. I relieved the stresses, I've reduced the environment, and I've reduced the hydrogen, okay? I've reduced the hardness. So this is hardness, HV, stress, and H2. By post-weld heat treatment, I do lots of good things. And if I properly post-weld heat treat, I probably won't get a hydrogen crack. And I told you about the Helms project, okay, about that. Now, how do you do it? What procedures do you use? Mike Baumforth was talking about the structural welding code yesterday. And here are some of the welding procedures per the structural welding code. Mike mentioned that you can take the certified welding engineer exam by either doing the standard of API 1104 or the structural welding code. There's another code, and he showed you the API 1104, which is this little thin thing, but actually it's more complex than this one. But the other code that's used most often is the ASME boiler and pressure vessel code. The problem with the ASME boiler and pressure vessel code is it's this thick, okay? If I take all the parts of the ASME boiler and pressure vessel code, you don't want to take a full day exam or a 3-hour exam on the boiler and pressure vessel code. You probably need about 5 years experience daily to understand the boiler and pressure vessel code. It's sort of like the US tax code. There is no one who understands the whole thing, okay? It's just a little too complex. It's the granddaddy code. It's like 105 years old, and it is the highest quality standard, because if a pressure vessel blows, it does really bad things, okay? Which leads me to another story, okay? So a few years ago, it's like 15 years ago, oh no, it's 20 years ago now. I'm sitting in my office. I was actually department head at the time, and I get this call that they had had an explosion up in North Andover. Okay? Yeah. It was only 16 tons, and it was only a quarter mile away. No, that was me. That was me. But, well, Ron may have done it later. They actually took me out of it because I became sort of a fact witness. I was one of the first two people down in the pit when they finally cleared out enough space, and they had a crane. The other guy was the chief engineer for Travelers Insurance, and I was the other guy. We were the two guys who got down there first to look around and say, a lot of trash down here. Okay, that's about all you can see, okay? But anyway, so this pressure vessel was a hot isostatic press, and it weighed about 300 tons. And it had a shape, it was threaded at the top. It was also threaded at the bottom, and the top cap and the bottom cap were 50 tons each, and the cylinder was 200 tons, as I remember. Okay, and this was about, I think it was about 10 or 12 inches right here, and it opened up here to about 28 inches at the top. And they had designed this in the mid-'80s on a Cray supercomputer. Okay, a Cray supercomputer is probably a $500 PC today. Okay, in terms of computing power, but they had done all the thermal stresses on this. This is a hot isostatic press, and if you take my thing on casting and it ends up a little bit on forging, I'll probably tell this story on that video, maybe in a little more detail. But it had been operating for a number of years. The inside diameter was 60 inches. And it was probably 20 feet tall or something on the inside. It wasn't a small vessel. It weighed 300 tons, the whole thing. It had been forged in Japan by Japan Steel Works. One of the only forges in the, well, one of the only places in the world that had both the steel making technology and a big enough forging press to do this. We had big forging presses, but Alcoa doesn't forge a lot of steel in Cleveland. Wyman Gordon, you'd have to make the steel over in Japan and then bring it over here. The Japanese have some, I don't know, maybe 30,000 ton forging presses. So they had forged the pieces, and you basically usually make something a little bit longer. They call it a prolongation on the forge. And so you can cut it off, and you can cut out tensile specimens, Sharpie impact specimens. You can do all your quality control tests on the heat treatment. So they did that, except it failed the mechanical properties after the heat treatment. Darn, okay? I could scrap it. That's only going to cost me $20–30 million. Or I can just reheat treat it. Now, how do you reheat treat it? Well, you don't have exactly the same chemistry. Well, you take something that's very similar to it. You can't weld on a prolongation, okay, on something like this. So you just take a piece of the material and you put it in next to it in the furnace, okay? But that doesn't cool exactly the same way as this piece. I mean, this one's 200 tons, this one might be 2 tons. And so they cool differently, they get different grain sizes. This one, the second time they heat treat it, passes. Great. Okay, ship it. Okay? So they do. And it goes out, and it's a hot isostatic press. They used to put Harley Davidson, in fact, I remember walking around the rubble of the building, okay, from the explosion, because it just wiped out the whole building. They had a bunch of Harley Davidson aluminum cylinders, and they would go through, they were cast cylinders, and they would hot isostatic press them to get rid of all the shrinkage porosity from the casting, because guess what? When you're on a Harley Davidson motorcycle, guess what's right between your knees? Okay, and if it blows up, okay, not a good day. So they have very stringent quality control standards for these piston cylinders or cylinders. So they put in a bunch of these in a rack and they heat treat it. It takes about a day to do a heat treatment. In a furnace like this, probably costs a couple of $1,000s an hour. So you're talking, well, maybe only $1,000 an hour back then. But so you might be talking $25,000 heat treatment. So you put more than one cylinder in, but you know, you put a bunch of cylinders in. They also, it was very convenient, it was 60 inches, and that was just big enough for all the discs that Pratt & Whitney and General Electric and everybody else were going to make some of the big jet engines. This thing went, and it was the only one in the world of this size for 3 months. Fortunately, people were building another one because they were starting to, all the jet engines, they were going into high bypass engines and stuff, you know, big fat engines. And this thing couldn't keep up with all the work that was being thrown at it. So about 3 years before, they had started ordering another one. And fortunately, when this thing let go, the other one came on stream 3 months later. Otherwise, it would have been 3 years before anyone in the world could have built an engine. Pratt & Whitney, Rolls-Royce. Think of the damages here. Okay? So fortunately, they had the other one almost ready to go. And they've replaced this one and other stuff. Because there was no other unit that had this, could take something that big around. But anyway, so it lets go. But why did it let go? Well, it turns out it's partly a hydrogen cracking story. It's not a welding story. But it's a hydrogen cracking story. Well, there were 3 things. For any type, in fact, they called it stress corrosion cracking, so I might as well call it stress corrosion cracking. In stress corrosion cracking, you have to have a stress, you have to have a susceptible, they call it susceptible microstructure. So it's not hardness, but it's sort of the same thing, okay? High hardness, susceptible microstructure, in this case, low toughness. Read low toughness there. And then you have to have a source of hydrogen, and you'll get stress corrosion cracking. Well, if you did the fracture mechanics on this thing originally, it had about a 12-inch critical flaw size if it had the toughness that it should have had when they did the heat treatment. But it didn't have that toughness. They took Sharpies out and it failed. So they redid it, and this little piece passed. And that little piece had enough toughness. But guess what? When they went out to test this thing out after it exploded, and one of these pieces, you're right, Jonathan, that piece right there, the crack ran right from that corner, stress concentration, and it just ripped off a piece about 1/3 of the way around. It weighed 16.5 tons, and it was found a 1/4 mile away. It took a lot of energy to move 16 tons a 1/4 mile. Another 5-ton piece, actually, we pieced the whole thing back together. Not actually, if you want, I'll tell you how you piece something like this back together. You don't piece it back together. You don't pick up 5-ton pieces. But it was in like 70 different pieces. So basically, the average piece, 200 tons, 70 pieces, that's 3 tons per piece, right? Pretty heavy. One 5-ton piece landed right on top of the operator's chair. It happened at 2 a.m. in the morning. This thing runs 24/7, right? The operator had just seconds before gotten up to go change one of their chart recorders, the paper on the chart recorder. If this had happened 15 seconds earlier, he would have been underneath the 5-ton piece. Okay? He was sort of rattled. Okay? But it landed right there next to him. Anyway, the chair was not in very good shape. Anyway, what happened? Fracture mechanics and everything, you try to design something like this for a leak before break. And a leak before break means if you get a crack, it will grow and grow until eventually it will create a leak in the vessel before the vessel just blows up as a brittle fracture. Okay, you want it to leak before it breaks. Break before leak's not good. Okay, no warning. In fact, on pressure vessels, if you read this ASME code for pressure vessels, they actually will impose duties to have a leak that warns you that the vessel, whatever's happening in the vessel, that it will leak before. And actually, typically, the leak, it has high pressure gas inside. This thing has 20,000 psi argon inside it. Okay, so the argon is compressed as a gas, but it has a density like liquid. Okay, if you start calculating 20,000 psi and stuff on argon. But anyway, you're using all this, and it should have had about a fracture, a leak before break of something. It should have leaked before break on the original design if it had the toughness. The toughness is equal to K1C is proportional to, well, I'll just call it, if you want to be precise, but it's not precise, square root of sigma square root of pi c. 1.12 for a planar crack. Stress times the square root of pi times half the crack length, okay? Or half the crack depth. A would be the crack depth. It should be about 10 inches or greater. Pi is the constant. Sigma is the stress. We know what the stress is when you're under 20,000 psi. They've done this finite element model. And